So the last section that we're going to cover this semester in discrete mathematics has to do with Euler paths and Hamilton paths. Euler paths, Hamilton paths. We want to provide some terminology first. First of all, what is a path of length n between two vertices? So let's say you have two vertices. Let u and v be vertices in a graph G. A path of length n from u to v. I meant to write of length n. A path of length, I did write length n. From u to v, that's what we're defining, from u to v. A path of length n from u to v is a sequence of edges, of edges. U is going to be your starting place. We're going to call that x0, comma x1. This will be your first edge, right? x0 to x1. Then your second edge will be x1 to x2. And so on and so forth, until you get to your last edge, xn minus 1 to xn. That'll be your last edge. And xn, remember, is your ending point. That's going to be v. So you have these n edges from u to v. It's a sequence of edges. That's all a path is. It's a sequence of edges. We represent the path by a sequence of vertices. So we're actually going to use vertices to represent the edges. We represent the path by a sequence of vertices. So all we do, we list the vertices at the starting place until the finishing place. So the first vertex will be u, which we call x0. Then x1, that'll be the second vertex. Then x2, that'll be the so on and so forth. Xn minus 1 until we end up at xn, and xn is the last vertex, it's the v value. So that sequence of vertices represents your path. It shows what vertices you're taking. So by looking at the vertices that you're taking, you can figure out what edges you're taking, right? A circuit, also sometimes you hear this called a cycle. So some books call this a cycle. Our book calls it a circuit, but you also hear it called a cycle. Is a path that begins and ends at the same vertex. Is a path that begins and ends at the same vertex. All right, so we want to define what is a simple path. Definition. A path is simple. Path is simple. So a sequence of edges is simple if no edge is repeated. So you're only allowed to list your edges once. You're not allowed to double back on edges. So no repeated edges. There's a definition. What does it mean for a undirected graph to be connected? So this is a graph without arrows. An undirected graph. It's a graph without arrows. An undirected graph, it's a graph without arrows, is connected That's what we're defining. if there is a path between every pair of vertices, if there is a path between every pair of vertices. And a graph is disconnected if there's not a path between every pair of vertices. So an undirected graph is disconnected so we're defining disconnected if there is not a path between every pair of vertices, if there is not a path between every pair of vertices. Now let's see if we can identify connected versus disconnected graphs. So, examples. Determine if the graph is connected or disconnected. Connected or disconnected? That's the question. All right, so here's my first graph. We're going to call these A, B, C, and then we'll have some more. Some new vertices and edges. We're going to have D, E, F. So the question is, this graph right here, this is a graph. Is this a connected graph or disconnected graph? Turns out that this graph, if you look carefully, it's disconnected. There's no way to get from the points D, E, and F to the other points A, B, and C. Right, there's no way to get to those. There's no path between. So if I call these the blue points, A, B, and C, there's no way to get from those points to the other points, well, let's call those the red points. There are no edges connecting the red vertices to the blue vertices, so it's disconnected. Number 2. About something like this. A, B, C, D, E. This one's definitely connected, right? It's definitely connected. Right, if I wanted to get from A to B, there's a path, I can go this way. If I wanted to get from A to C, there's a path, I can go this way. If I wanted to get from A to D, there's a path this way. No, it should have been blue. If I wanted to get from A to E, there's a path this way. That's just getting from A to there. So I can go between B and C, B and D, B and A, B and E. Yeah, I can go through. In any case, there's always a path between any two pair of vertices. Okay. That's just some background information. So, two of the big things we want to look at are what is an Euler path, what is a Hamilton path. What is an Euler path and what is a Hamilton path? So, an Euler path, that's what we want to define. Definition. An Euler path that's what we're defining in a graph G is a simple path containing every edge of G, Every edge of G. So let's think about that for a second. So first of all, it's simple. So that means you cannot visit edges more than one time. You only can visit edges once. You're not allowed to repeat edges. And it has to contain every edge of G. So in essence, what we're saying, an Euler path, that's a path that visits each edge exactly once. Visits each edge exactly once. That's what we're saying. You have to visit every edge exactly one time. Okay, what else do we want to define? We want to define what is a Euler circuit. An Euler circuit. That's what we're defining. Circuit. That didn't write too well, did it? An Euler circuit in a graph G is a simple circuit. So remember, simple means you can only visit every edge at most once. You can't double visit edges. A circuit means you have to begin and end in the same position. So it's a simple circuit containing every edge. So if you break that down, what does that actually mean? A simple circuit containing every edge. It means it visits each edge exactly once, visits every edge exactly once. It's the first thing. And second of all, it has to begin and end in the same place. Begin and end in the same place. Begins and ends at the same vertex. So I guess the question is, what exactly is the difference between an Euler circuit and an Euler trail, or Euler path? Sometimes they call an Euler path an Euler trail. An Euler path, or an Euler trail, it's a path that visits every edge exactly once. An Euler circuit does the same thing. It's a path that visits every edge exactly once, but you have to begin and end at the same place. So the circuit means it begins and ends at the same place. Okay. So, very famous problem. Going back to the 1700s, we have the famous mathematician Leonhard Euler, right? Leonhard Euler. Leonhard Euler. So Leonhard Euler is probably one of the all-time great mathematicians. Many people place him as number one of all time. So he was in the city of Koenigsberg, which today is called Kaliningrad. So Koenigsberg was the capital of the Kingdom of Prussia. The Kingdom of Prussia was a German kingdom, which today would be situated along the Baltic Sea. So the Prussian Empire united Germany in the 1870s, and they formed the German Empire. And then under the Third Reich, under Adolf Hitler, they fought with the Russian Soviet Union, and the Soviets conquered Prussia and the city of Koenigsberg. That was one of their main targets. They had two big targets. They wanted to destroy Berlin, number one, and number two, they wanted to destroy Koenigsberg. So today you'll actually see Koenigsberg is Kaliningrad. Well, anyway, Leonhard Euler was there in the city. And the city sits on the river here. So I'm going to draw a little map here. And here on the west side is the Baltic Sea. Baltic Sea. And here's called the Pregel River. So in German, it would have been Pregel River. Now, nowadays, they call it the Pregulia River, right? It's Russian, Pregulia. So you have this island here, And then you have this larger island down here. And you had some bridges. Here, 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 and here, going across the river to this island. Then you had a bridge here connecting these two islands. And you had bridges connecting this island to the mainland. So what Euler asks, he asked the following question. Was it possible to walk through the city of Koenigsberg? So the city of Koenigsberg was on both sides. It spanned the river here, Koenigsberg. And it was here in the middle as well, where these islands were. That's the city of Koenigsberg. It spanned the north and south mainland and the islands. He asked the question, is it possible to walk across every single bridge exactly one time without double crossing any bridge? You don't want to double cross any bridge. So you can try doing it, right? Let's see if we can try. Can we do it? Is there any way possible to do this? So I could start here, and I could go down here and cross here. And I could, what could I do? I could maybe try crossing here and then here and here. But then I don't cross the other two bridges in the north, right? So that doesn't quite work. So you can try lots of things. So I'll leave that up to you. What do you think? Do you think it is possible to cross every single bridge exactly one time while walking through the city of Koenigsberg? Exactly once. Just visit every bridge once. I'll leave that up to you. And we'll reveal our answer in a later video.